So we were talking about co-reference resolution in our last lecture. So there we saw that what is meant by co-reference, and we saw some examples of that. We also introduced the concepts of anaphora and cataphora. Then we looked at different techniques in which we can identify, or we can. So if we look at given text and we have to identify all the co-references from there, it's something like a clustering. So each co-reference chain will contain a list of spans or segments or phrases from the input, and they refer to each other. So in that way, it's a cluster, or it can be considered to be an equivalence class. Yes, and when we say cluster, it's a non-overlapping cluster. So, and given a text, there can be multiple such non-overlapping clusters, which essentially talk about the different entities which are being mentioned and discussed about in the underlying text. So we saw some techniques on how to reduce the number of candidates that we consider for the clustering approach, and some data sets we also looked at a specific task called Vinograd Schema Challenge, which is a bit difficult task for a machine to handle because it requires some common sense reasoning as well as a deeper natural language understanding. And this is also used to evaluate the power of many of the modern models which are being proposed for language understanding, text embedding, and so on. Now, we concluded by looking at some kind of features that can be used for a feature-based algorithm for co-reference resolution. So today, in the first part of the lecture, what we will do is we'll look at some neural algorithms for co-reference resolution. We'll also look at some kind of evaluation metrics to measure the performance of these co-reference resolution algorithms. So we'll first talk about evaluation measures. So again, the task of co-reference resolution is where given an input text, we want to identify the different mentions in the text which are co-reference to each other. So as we said, essentially, finally, we have some kind of clustering structure coming out of the text. And for evaluation, we also expect a list of the co-reference chains, ground truth co-reference chains, to be available as a reference, right? So we have one set of clusters which the algorithm has given, and another set of clusters which are given by the annotated data. So the first technique here is called MUC or MUCF measure, which is very similar to something like the F measure, but what are the different things that we are comparing that changes? So let me see if I can scribble on the slide. So suppose we have H as a clusters, the clusters which are given by the algorithm. So H can be the hypothesis, something that the algorithm is given, and R contains the reference clusters. So inside a cluster, there are spans which are co-referents. So suppose it has three clusters, H1, H2, and H3. And inside H1, there are three phrases. Inside H2, there is one phrase. And then inside H3, there are five. Now, let us consider that in R, we have two clusters. So here we have two of them, and here we have a few more of them. Now, each of these entries we have their names. Say, for example, here we have R11, and here we have R12, and here we have R21, 2, 1, 2, 3, 4, 5, 6, 7, R27. Well, these are the names, identifiers for the mentions. And here we have H1, 1, 2, H13. Here we have H21, only one entry. And here we have H31 to H35. Okay. Well, so next and obviously, since they're operating on the same input text, some of the HIJs would be equal to some of the RKLs. So yeah, so that's what we expect. So what we do in this MUC F measure is that you check how many links are common. Okay. So from these clustering structures, you identify the edges. Say suppose this is one edge which is matching with this edge here, and this edge here is matching with this edge here. We also see, this edge here is matching with this edge here. Okay. Now these edges, if we give some numbers, like this is edge 1, which is matching with this edge 1. This is edge 2, which is matching with this edge 2, and this is edge 3, which is matching with this edge 3. So based on this, we compute the MUC F measure. So here in H, the number of possible edges from this cluster will be 3. From here, there is no edge, and from here there are 5 nodes. So 5C2, which is 10 total edges, will be there. So from the prediction of the algorithm, we have 5 plus 3, which is 8 edges we get. And from here, we have 7C2, which is 21, and 22 different edges which are there. Okay, so now if we consider the edge list that you get from H and the edge list that you get from R. So this is the edge list from H. And similarly, you get edge list from R. You essentially try to compute a precision and recall based on these. So precision will be how many edges are in common between them, EH and ER, divided by how many edges are there in the prediction, okay, which is 8. So that will be the precision, and the recall will be how many edges are in common between them. That will be the numerator, and the denominator will contain how many edges are there in the reference. So now you have the precision and recall, and then you can compute the F measure from there. Okay. So this is how MUC is computed. It is link based. So you run your algorithm, you get the clusters. Each cluster has certain mentions, and you identify the edges between the mentions. And same you do for the clusters which are there in the reference. Now the edge list that you get from these hypotheses and references, from that you identify the number of common links, and from that you compute the precision and recall. And the average, harmonic mean of them will be the F measure. So this is one metric which is used for evaluation of co-reference resolution algorithms. And then the next measure, which is B3. So it is mention based. For each mention in the reference chain, that is each cluster, each individual cluster, we compute a precision recall. And we take a weighted sum over all the n mentions in the document to compute the precision and recall. So how does it work? Suppose you take one mention, I, okay, and you identify the ground truth coreference chain that contains it, and that same mention is in the this reference chain in the hypothesis. Now you you identify the reference chain from the hypothesis and reference chain from the uh, reference, and then you try to find the common elements in this as well as this. So essentially between these two, you try to identify the precision and recall between this cluster and this cluster. So the numerator will be how many entries or how many mentions here match with the mentions here. So that is the intersection that we are trying to find out. And for precision, you divide that number by the number of elements here. For recall, you divide by the numbers here. Okay, so that way you find the precision and recall for that particular mention. And then you can do, I mean, an average of the scores that you get when, so average over all mentions I in the input text. So you take the average precision for each mention I, and similarly the average recall for each mention I. Then based on these average precisions and average recalls, you compute the F measure. So that will be B3. So we talked about two measures. The first one is MUC, which is link based. The second one is mention based. Both finally boil down to computing precision recalls, and then yeah, F measure is used. And there are other composite measures which take the average of MUC and P3. Okay, any
Sir,
queries?
one question here. What is how are we calculating the recall in B3?
Okay, so recall will be the number of mentions that are common between this one, that is the reference cluster that contains I, and the number of mentions which are there in the hypothesis that contains I. So if there are two here and we have 5 in this cluster, and suppose both these are present here, so the numerator becomes 2 and the denominator becomes how many are there in the reference in the reference cluster, so which is 2. On the other hand, the precision will be the number of common mentions in this as well as this, and divided by the number of mentions which are there in the this cluster, so which will be 5 here. So this is for this specific mention, and you repeat this for each individual mentions here and take the average. So that will give you the average recall.
Okay, got it.
Sir, why are we comparing these two? How do we like what's the mention here? Is it the word what we are searching in the cluster?
So mentions are Mentions are the different candidates which could be there as the co-references. So if you look at this one, this sentence, the trophy did fit to the suitcase because it was too large. The mentions are the phrases which can actually talk about an entity of interest. So the trophy is one mention, suitcase is one mention, and it is another mention. They refer to some entity. So given an input text, one way of saying identifying the mentions could be like you get all the phrases that you can extract from here. So that can be your mention list. Okay. However, the algorithms typically identify the nouns, the pronouns, and yeah, named entities. So that will again fall under the larger category of nouns. So these things become the mentions, and the other things we actually do not consider that much.
These won't be labeled mentions in the data set. We need to find it by using some package, is it?
So if you think of the data sets like this, so
Mhm.
there the mentions will be present. But when you get a new text, you for inferencing, you may not have the mentions indicated there.
These are your co-reference chain, right? It says that it starts here, it ends here. Do we call the same thing as mention as well, or mention is just the noun and pronoun?
So each candidate that you consider for
Mhm.
your co-reference resolution algorithm, that becomes a mention. So here, everything that is there in the co-reference chain is mentioned definitely. And then you can also have something like Chapter 11, Federal Bankruptcy Code. These are some additional mentions. So this you have to identify from the data.
Okay. Okay, and in the output, when we compare, like we need to find out the clusters. You say each chain is each chain ID is one cluster, right? Co-reference
Yes,
chain ID.
yes.
Oh, okay. And in the first approach where we were finding the edges, is it like graph-based network? Do we train any, like how do we like practically how do we create the edge and
You run the
like?
co-reference resolution algorithm, and suppose it these are the outputs that are given by the co-reference algorithm. So it says
Mhm.
the chain one contains this Eagle Clothes Corporation, then it's the retailer. Uh, yeah. So these are the co-reference. These are co-references.
Yeah.
Then you create a set with these entries, essentially that chain. And if there are four entries there in the cluster, automatically there will be four C2 edges.
Oh, so all entities combined together are forming edges.
All entities in a chain, that is a
Okay.
cluster. And in a cluster, everything is equivalent. So everything is connected with everybody else.
And in case of that first algorithm, we are finding the edges for each cluster from the hypothesis and also the reference, right? We compare each cluster from each.
Right.
To,
Okay. So that is the evaluation measure. Now let us talk about some advanced algorithms for finding the clusters.
Sir, one question.
Yeah.
Sir, a single mention can be there in multiple clusters in Edge. Then,
Yes.
how do we take the B3 score there?
B3 is fine, but MUC, so if there are too many singleton clusters, in that case, in MUC, these things can be preferred because I mean, there is no additional age that you are getting here. So there is no chance of getting any mistake.
Like if we consider a single mention it, then
Mhm.
it may refer to may come in multiple context in a document.
I
So
see.
it may be present in multiple this chain co-reference chain.
So
So
actually,
yeah.
yeah, I got your point. So uh, so it's not only the word. So when we do these evaluations, we also identify the token number, the position. So that way we distinguish the different occurrences of it and which coreference chain they belong to.
So basically, it's not a single mention. We consider it differently as per their occurrence, as per its occurrence.
Yes. They're not the words as such, they're the tokens, the exact appearance in the text. Okay, so one way in which the coreference identification can be done is mentioned by using mention pair architecture. So suppose this is the input, Victoria Chen. Okay, I forgot to give the incomplete text. So suppose these are some excerpts from a sentence, and these are the different nouns or named entities or pronouns. We have said that, okay, these will be the mentions that we are considering. And finally, mention pair architecture, the way it works is from here, it looks at all pairs. So if there are n mentions, in candidate mentions, we'll get NC2 pairs. So for each of these NC2 pairs, it tries to predict whether there is a coreference structure between them or not. So in this example, suppose you have Victoria Chain and she. So according to ground truth, this is a coreference. Okay, so the algorithm will try to give a high value for this probability. On the other hand, suppose her and megabucks backing, or she and megabucks backing. So this is a negative example. There is no, when these two are not connected. So the probability value expected for this pair will be less. So for a pair of mentions, it predicts whether it is a coreference or not, and it can be modeled as a classifier which can be trained. So idea wise, this is simple. So you have an input, you have a first phase of the algorithm which can identify the mentions, and then for each of them it can try to predict what is the probability that they are coreferences. And there could be approaches where these two things are not segregated into stage 1 and stage 2, but there is a combined thing that happens, something like an end-to-end training of this model. So this mentioned pair, and then there is something called mention. Sorry, this one is mentioned. So this should be mention ranking architecture. Mention rank architecture, mention ranking architecture. So here what it does is, instead of getting the probability for each mention, it tries to say that wherever you have a correct mention, so for those things, the probability value should be higher against the values which have the incorrect mentions. Okay. So this is the, and you incorporate this data in your learning process, in your loss function or whatever. So for a pair of mentions, it ranks them based on how likely they are to be co-references. So right, so finally it gives an ordering, and yes, the loss function is defined accordingly. So we'll look at neural algorithms for that. So the first algorithm here, which considers the text, and suppose there are capital T number of tokens in the text. So we have x1 to xt as the tokens. Now the number of possible spans that you can consider is t into t minus 1 by 2. So we have x1 to xt, and each span is nothing but say I call it capital X, or a S is a span, and this S comprises of some consecutive tokens from the input. So xi plus 1, xi plus 2, and like that it goes until ij. And of course, here we have I less than equal to j. Okay. And it is easy to see that the total number of pairs, the total number of spans like this will be t into t minus 1 by 2. Now, the obvious concern is that if we have a text, any reasonable size text will give a large number of these spans. So suppose we have a small text of say 100 words or 200 words. This actually explodes the number of spans. So often to get rid of that, what people do is they can impose some length restriction. So typically we won't expect the spans to be larger than say 5 or 6 words. So there could be movie names which are slightly longer, but in most of the cases what we will see is that the span lengths will be limited. And secondly, if you also have some good quality uh, pause tagger or named entity recognizer for the language, then you can also extract the different named entities or the nouns, which you can also say that, okay, anything that is not any form of noun that will not consider, anything that is not a named entity that will not consider. So apart from the length restrictions, these things could be some ways in which you can reduce the number of mentions that you'll be considering as part of this algorithm. Then what it does is it orders the spans in lexicographic manner. Okay, so suppose x12 is a span, then x14 is a span, x23 is a span, x78 is a span. So you have a lexicographic ordering or dictionary based ordering of lexicographic ordering of the spans. Then the ith span yi ranges from start I to end I. In the next slide, the formulas that we have or the equations that we have this set. So if this is the span number m, I'll say that the span m starts at I and ends at j. So, and for each span, the possible antecedents, we know what is antecedent, right? So the references to the text that happened, that has occurred before the current mention, those are antecedents. Possible antecedents are from epsilon 1 to I minus 1. So we are ordering the spans like S1, S2, S3, like S4, and like that. And say S1 is this one, S2 is this one, S3 is this one, S4 is this one. So for S4, the antecedents could be from S1, S2, S3. For S3, the antecedents could be from S1, S2. So for S4, the possible antecedents will be from S1, S2, S3, which is I minus 1, if it is Si, and epsilon. Epsilon is a dummy span, which is output when Y is not an entity mention. Algorithms can go wrong, or there could be, we saw that there are some pronouns which could be non-anaphoric, like it is going to rain, and it does not refer to anything here. Or it could be the first mention, first time specific entity is being mentioned. So that means there is no antecedent, but we can get something which will come later. So this is the overall structure and terminology. We are given a text. We consider the all possible spans, but this may be too large. So we reduce that number by having some rules. And then we order the spans in lexicographic manner. And for ith span, this is I. Say suppose we are talking about S4 where I equal to 4, that is the ith span. It ranges from start I to end I. So start I is 7, end I is 8. And for yi, the possible antecedents are from epsilon and 1 to I minus 1. epsilon is a dummy span, which is output when there's not an entry mention, or is a span but not co-referent to any previous span. So this is one. Yes.
Sir, here X are sentences or X are just simple words?
These are the tokens.
Okay.
These are the tokens. So these are X's. Suppose our input is General Electric said that postal service contacted the company. So X1 is
Sir,
General.
how to handle nested thing there?
What
Nested
nested
span?
There is no special consideration about nested span.
But we are doing this lexicographical ordering. There we'll have to consider, right?
No. No.
Okay. Okay, sir. Go ahead.
So this is the input. So so this paper is from 2017. Later, this by LSTM block can be replaced by any other algorithm. So you give the input, you pass it through some type of contextual embedder, and you get the output. Representation for each token from here. Then suppose we're talking about two spans, yi and yj. So we compute a score for this pair, ij pair, and this pair, this score is decomposed into three subscores: the mention score for I, the mention score for j, and the affinity score between I and j. So the mention score, in some sense, tries to capture whether something is actually a mention or not. So how strong the algorithm's confidence is that it is a mention. So it is captured by this Sn, and Sa is given to spans yi and yj. What is the chance that they are related or they are co-reference? And score is 0 for the dummy antecedent epsilon. So for epsilon, Sm is 0. So what happens is that so before coming to this equation, just look at this because the terminologies are mentioned here. So this token, you pass through this architecture, you get a representation from here, and suppose you know that yi is for general and electric. Huh? So yeah, so from this you can capture the span, a representation from the span. So the representation from the span is given by this. So x star start I, x star end I. So there can be some spans which have, say, multiple words, right? So you get the representation for the first token of the span, the last token of the span. So these you concatenate, and then there is a representation for that entire span. And for that, an attention-based framework is used. So that's the representation of the entire span. And then this phi I is a kind of length embedding. Okay? So what is the length of I? Based on that, there is some function that transforms it to get an embedding, and you concatenate all of them to get a representation for the span. Now, once you get the representation for the span, you pass it through a feed-forward neural network to get the mention score for this span. So, and that takes care of this component of the lecture. You replace I by j, you get this one. And for the third thing is aij, what you do is you get this representation for span I, representation for span j, and this one can be the element-wise overlap or element-wise multiplication. And this could be some other function which can be based on the lengths of these spans. Again, you concatenate all these features, pass it through feed-forward neural network, and you can multiply it with some weight so that the scales and other things are adjusted accordingly. And this gives you the mention score for the pair Sij. Now, this Sij, and you have the reference, like what are the different things which are in the same co-reference chain or so on. So based on that, you can have a loss function, you backpropagate and you learn this algorithm. And finally, to decide whether to while you during the inference, you give an input, you follow all this process, and you get the mention the final scores for the co-references. You can do some kind of thresholding to determine whether to construct the co-reference chains. Okay, so let me know if there are any doubts. So the link to the paper is also mentioned. I can go through it. Okay.
Sir, on the picture it shows the input, the text, but here GI is like your token and also two more extra thing, right?
What the text? What is
I know, like as per the model here, it says that input is General Electric set, that those are the inputs, and but it GI is the actual input, right? Where you have X start and X end of each token. So my question is, like, how the input we are giving to the model, is it like per token wise, GI is for each token, uh, I mean, or is it per chain where it starts and end?
this input? You give the text as input. Then this text passes through this architecture, which gives contextual embeddings. And then you have so we're talking about span I. The span I is General Electric. To start I is 1, end I is 2. So you get the contextual representation for X1, which is general. So which is this one. Then you get
So
the
that is
contextual.
GI.
Yeah, so this is X, and here we have G.
Oh.
For computing G, we need the X's.
Okay, so in there we also need this phi I and xi cap. How we are getting those things at that layer?
Xi is the context is an attention-based representation, which is described here. And for getting xi hat, you need to know the x stars, right? So this x hat will operate on these x stars in this manner. Simply you check the attention, so this will get, and this will be some length-based encoding.
Okay, yeah, thank you.
Okay, so the overall architecture, as long as the high-level idea is clear, I think that that should be fine. And then we'll talk about.
So one question here. So when we have the attention weights already, do we really need this to input the start and extend the complete word to?
So you mean that we have x hat, which is obtained by applying attention and then making use of these x stars anyways. So do we
Yeah.
need to have this explicitly? Yes. So
Yeah.
sometimes what happens is that the span representation is for the entire thing, but the starting and end part also sometimes plays an important role in determining other things. I mean, that was the motivation due to which they have it. I don't think they have reported the experiments where they do not have X start I and X star end I. But yeah,
Because attention will anyway capture all those information, right? I was curious about that. Okay, thanks.
Sir, here in this, can you go? So when we say start I and end I, then do we consider entire token between start and end, and or only the start and end point? Like
only
if
start and only stand.
like for general and postal, it will be only the this uh, X star for general and X star for postal.
That's correct. Yeah. So suppose we have the postal service. No, this is a mention, and this is a candidate. So X star will be the representation for the X star end I will be the representation for service, and Xi hat will be the overall representation for this entire thing. So, the next part, just 1 second. In the previous slide, when we had this phi ij, this phi ij can actually capture a few other things as well, which could be like the distance between these two mentions. If they are very far apart or close by, that distance is there in phi ij. And for individual thing like phi I, it can be like. Okay, so now let us move on. So then there was one approach that was proposed in one uh, paper. The idea was interesting. So that was that you pose that code reference resolution as a QA task, because such kind of reasoning, like synonymy, word knowledge, syntactic variation, uh, so these kinds of things required to answer the questions are, yeah. So based on that, if you can frame the questions appropriately, I think next slide has an example. Then you can actually leverage the existing QA model. So there are not many datasets for code reference resolution, as you understand that it's a bit difficult to construct, and difficult in the sense requires understanding of a larger text, and a lot of human analysis will be needed. On the other hand, there are already available large number of QA question answering datasets and frameworks. So if we can somehow pose that code reference resolution problem as a question answering problem, we can make use of those resources, the datasets, algorithms, and so on. If this work and reference is then the last slide, in the final slide, that means. So suppose you have different sentences. Okay, Sam moved to garden, Sam went to kitchen, Sam dropped the apple there. Now there is a first phase of the algorithm that identifies there is something that can refer to uh, other mentions in the text earlier. So now since this is there, from it we come up with a question. So where? So the question generation part will pose this as a question like where is Sam? So next what it does is for each sentence, it gets a representation. Okay? And suppose this can be obtained using any architecture, say LSTM, YLSTM, Elmo, BERT, other things. So for sentence 1, the representation is M1. Sentence 2, the representation is M2. Sentence 3, the representation is M3. And for this question, you also get a representation U1. Next, what you do is you check how similar this is with M1, M2, and M3. And those similarity scores can be dot product followed by softmax. So it can be like 0.1, 0.7, 0.2. Next, you modify the representation of the question. The representation of the question is now modified as this 0.1 into M1, 0.7 plus 0.7 into M2 plus 0.2 into M3. This one. And you add that with U1 to get a refined representation for U2. And you do this multiple times. And after you determine, so that's the depth of this. And after that, you then actually make use of a question answering model to identify what is the span from here that the answer to this question. So this is sometimes referred to as a memory network. you have the representations of the individual sentences, then you find the alignment of this question with them, updates the representation of E1, keep doing it multiple times, and finally you make use of a question answering model to get an answer to this question. So this is one work. And then there was one more work which says that query-based span prediction. So the same problem, they again posed it in a different way. So they have a mention proposal model.
Sorry to interrupt. In the previous slide, how do we get this question? Like, I didn't get it.
So these questions can be generated based on templates, or there could be a question generation model.
Okay, so the questions will be generated separately, and then we have to use that question to.
Right.
Okay.
An answer is part of the data set.
Answer is part of the data set.
The level.
So if you have some pre-trained models for question answering, that can be used. Finally, the end task is here the codefinance resolution, right? So finally, we'll be evaluating on a codefinance data set only. So there in that data set, you'll have the reference for there.
Yeah, but to ask the question and get the answer from the data set, we should have, we should pass that context here, right? Or we pass the whole data set and then we ask the question.
For each example from this codefinance resolution, so that can be converted into a question answering, and then existing models for question answering can be used. So if you have that codefinance chain ID, so there along with there this keychain is a code reference. Then keychain is the answer to this question there.
Okay, but then it also has some linguistic overhead to create those things, right? Question and answer.
Yeah, so this is one alternative way of looking at the problem. So that was the excitement that this paper generated. Yeah.
Okay, got it.
The next part, what it does is given an input, so it has a mention proposal module. So you give an input text, and there is some mention proposal module, which can be a neural network, which highlights the different mentions which are there in this text. So earlier, what we were saying is that you identify all spans, you eliminate some of them based on length or their part of speech or other things. And here it says that, okay, you do not need to do all those things. Simply there will be a neural architecture that will highlight, that will give us what is the list of mentions here. Okay. Next, from there so this is the output of that, the list of mentions. Next, we have a question passage kind of pair. So you look at the portion, suppose I here is that first mention. So this I pose like a query. How do I construct the query? That I was hired to do some Christmas music. So you write it as, since I has been detected as a mention, you write mention, I/mention was hired to do a Christmas music. So this is the question, this is the query. So the model, and then you can have something like what are the different entities that I is referring to. Then second question for the word my cat or mention is that I bought my cat with me to the studio. I brought my cat with me to the studio. So I brought this, my cat is the current mention in question. So this is also included inside the mention and /mention tags. And this passage remains the same. And given this question and given this passage, they expect the model to give these answers. Now, this was again, there was a question asked asked earlier, like what are the different, say suppose the same word I or it occurs at multiple places. So how do we distinguish among them? So actually they are different, and yeah, so essentially we operate at token level. So that's why for each of them, so you can see multiple I's coming here, multiple me's coming here. So again, this is one more way of viewing the codependency resolution problem. So this entire thing, I mean, as long as you get the overall idea, high level idea of how this is framed, that is sufficient. So below we have, I have mentioned these equations from the paper. So the paper link will be there in the final slide. But at a high level, again, this also uh, gets a span score. And there they have some representation of the beginning part, the first word, and some representation for the end word. And this again connects with another question that we had earlier. Like, since we have the embedding for the begin and the contextual embedding of the end character, uh, and then we were also having the attention-based representation for the entire span. So some information already consumed or captured inside that attention. Okay. So do we really need to have both of them? So here what they have done is just first and the last tokens embeddings they have got, and they are contextual embeddings. So they are in some ways getting the information from the surrounding tokens also. And this thing they are passing through a neural network to get the mention score for that. And then they also used a BIO encoding to identify, for a span where it begins, where it ends. Based on that also they have something. Some terminologies will be in there, so that by referring to the paper we can get. And again, in the earlier work also we had SMI, SMJ, and SAIJ. So SAIJ also they have here. So that they compute using this. So here they make use of the BIO structure. So log probability that is BI. What is the probability that that is a beginning of the that has a begin time, because the span is from BI to EI, right? So that starts at BI. So what is the probability that BI will have a token B? And then for BI plus than to EI, they should have the I tag. So that score they capture. So like that, the this one is co-reference resolution as query-based span prediction. Yeah, so this is the paper, hyperlink is there. And for the previous one, co-reference resolution using memory network, that also will be. I think it is this one. So that is on co-reference resolution. And then there are newer algorithms which are coming. You can use different kinds of architecture frameworks for solving this and so on. So high level, that is what is co-reference resolution, and we looked at some ways of identifying co-references based on feature-based techniques. We looked at some ways of approaching the problem of co-reference resolution directly, or by posing it as some other kinds of tasks for which a larger amount of data are available, so that some of those models can have a warm start. And we also looked at some evaluation metrics for co-reference resolution. So let us know if there are any queries. So we'll take up a new topic after this one.
In the last one, that question answering model, is it like two models are there? First we have the left one, right, where we have I was hired, this one, the most left, where we predict all the mentions. After that mention, we have this question answer model. So what's the input of this? Like, mention is the input for this? Is it the question? My question is on this, what kind of QA model will be there?
What kind of QA model? Do you know what kind of? So this could be considered as the model architecture.
So
You have the mentions, and then you are having the co-reference, right? You have to identify. So for each of the mentions, you have this. for each mention pair, you'll have I and J.
Mhm.
So based on that, you can have the.
Yeah, but
So let me.
even questions. Go ahead.
Yeah, you complete your question.
Yeah, so my question was that now how do we like input questions and also the mention, how do we train the network, the QA network there?
Let me open that. Okay, so they did not pose it actually as a question answering kind of system, like what how they do it. I think that was an incorrect statement that he made, but they have it some kind as some kind of you have a query and then you want to get it resolved by looking at a reference text. So like that they do. And the internal modeling is based on these operations which are represented by this formula. So
Sir, is it like given a query sentence? Um, we are trying to find all the sentences which are linked with it, and then then see whether the mentions present in the sentence predicted by the model is actually the correct mention or not.
right, of that sort. The query contains the mention for which we want to identify related mentions. And yes, by looking at that and the entire passage, we try to come up with this. So yes, what you said is right. Okay, so I would suggest that if you are want to know more about this one, you can go through the paper. So there are a lot of other optimization tricks or engineering tricks that needed to be here because yeah, I mean, as you can understand, it's quite a complicated model and the number of
So
mentions.
here we have two separate set of models. One NLP model is predicting the mentions, and second question answer model is for evaluation purpose only.
But this entire thing they train together.
So the mention, which is the first model, the mention prediction model. So it is also interacting with question answer module
Yes. So this is the.
during the training.
Hmm.
Then in that case, we need to give the answer to each of our training questions.
Yes. So let me see if they're explicitly forming it as a question or internally they're handling it using some parameters. Overall architecture in passage first where in the mention proposal module 3.3 to obtain candidate mention. So there is a mention proposal module. So this is the mention proposal module and where we present the first and last token item. We only keep up to lambda n spans with the highest mention scores. Yes, so this algorithm produces a list of spans which can be considered as mentions. Now, given the mention, so that is the second stage. Then the mention linking module is used to extract co-referent mentions from the passage for each proposed mention. and co-reference clusters are obtained using the scores produced. Now this is the mention linking, but given a mention EI proposed by the mention proposal network, the role of the mention linking network is to give the scores for any text span EIJ, indicating whether they are co-referent. We propose to use the question answering framework as the backbone to compute SAJ. It operates on the triplet context, query, and answers. The context is the input document. The query is constructed as follows. Okay, they construct this query explicitly only, and then following this query as a single packed sequence, right? And since I mentioned can have multiple co-referent mentions, and then they have the BIO encoding. So question, then some a special token, then the context. This goes to a BERT like span BERT or some other kind of thing. And for each of the tokens, whatever representation finally we get, from that we get the BIO encoding.
Yeah, got it.
Yes.
So here is the key, like they are giving both context, I mean input, and also mention in the question, and from that they are predicting the score.
Right.
Yeah, got it. Thank you.
Okay, so it's 9. Let us start the next topic, and yeah, maybe after 15 minutes we'll go for a break. So this topic is discourse in NLP. So again, it's a task, it's a problem which requires a deeper understanding of the text. So what is meant by discourse? We'll come to that. So suppose we look at this pair of sentences. So it says John took a train from Paris to Istanbul. He likes spinach. So what do you think? Does it make sense?
No.
These are non sequitur statements.
Then suppose we have another one which says Jane took a train from Paris to Istanbul. She had to attend a conference. Okay, now what do you think? Does this one make sense?
Yes.
So I guess it was not difficult for us to get an answer or to determine whether it makes sense or not.
Yes.
Why so? Because we have the common sense knowledge, we have world knowledge, and based on that, say that okay, somebody is going to Istanbul because there is some task to be attended. Right, that makes sense. On the other hand, the first one, if we really want to, I mean, there can be really very rare scenario which could be something like Istanbul has very high quality spinach that this person wants to get. But these are very far-fetched connections. So when we humans look at input text based on our common sense reasoning, based on our understanding of the world knowledge, we can say whether something makes sense or something does not make sense. So typically when we look at text, and when we say text, maybe slightly longer text which can span across, which can contain multiple sentences and so on. So we'll expect there is some kind of relation with the different things which are being said in the text that should exist. So this is sometimes called, or this is referred to as coherence in that in this NLP community. So if there is no such connection, if things appear to be really ad hoc or arbit, we say that okay, it is incoherent. There is no coherence in the text. On the other hand, if there is a text where there's a nice flow of information and everything stands together, then it's a coherent text for us. So coherence is a very important property in language. Now let us look at another set of sentences. Like John wanted to buy a piano for his living room. Jenny also wanted to buy a piano. He went to the piano store. It was nearby. The living room was on the second floor. She didn't find anything she liked. The piano he bought was hard to get up to that floor. So these is the paragraph in this sequence of sentences. Now, again, what do you think? Does it make sense? Is it coherent? It being able to convey the idea. So I guess it is being a little difficult as compared to the previous example, because we have more number of sentences and there are quite a few entities which are being talked about, and there is no entities are being referred again and again and all that. So now let me look at the another example and then we'll come back to this question. Does this one make sense? See, John wanted to buy a piano for his living room. He went to the piano store. It was nearby. The living room was on the second floor. The piano he bought was hard to get up to that floor. Jenny also wanted to buy a piano. She didn't find anything she liked. Now, does the second one make sense?
Yes. Yeah. Yes.
Yes.
And what about the first one?
First one is jumbled.
Right. So, so again, from these two inputs, now we see that the second one actually is a good and coherent paragraph. On the other hand, the first one is not. And the reason is, so whenever we see some kind of passage, large volume of text, so these are actually called discourse if they have coherence in them. So this is a proper discourse, whereas this is not. So whenever we have a discourse, that focuses on some salient entities. Of course, so there are quite a few entities which are being talked about here: John, Jane, piano store, living room, second floor, and all that. So it focuses on some of those entities, and it does not change focus back and forth between multiple entities. So this part, like not changing focus back and forth between multiple entities, that was there in the second example. But for the first one, it kept jumping from here and there, as some of you mentioned. That's why the thing appeared very jumbled. So I'm talking about John, then piano, then Jenny, then he means I believe it's referring to John. Then we're talking about the store. Then we're talking about the living room, and again we're coming back to Jenny, and there is no connection between these. And then again we are talking about the second floor of the house. So things were going in a haphazard manner, back and forth mentions. Okay, so if you look at the different tasks in NLP and where do they need to focus, now this attention does not relate with the self-attention thing that we talk about in transformer. So we need to focus inside a sentence. Our focus needs to be limited inside a sentence for certain tasks like name-related recognition, part of speech tagging, and so on. And next class we'll talk about parsing. So there also we'll see that when we talk about different kinds of parsing techniques, we mostly focus inside a sentence. On the other hand, estimation of coherence, understanding whether something is a proper discourse or not, or understanding discourse level details. This requires us to look at across the sentences, as we saw in the previous examples. So coherent structure needs to look at across the sentences, and that is why it is again a deeper natural language understanding problem. And similarly, co-reference resolution will all answer under that category. So now what is a discourse? So a discourse consists of co-located, structured, and coherent group of sentences. Okay. And what makes something a discourse as opposed to a set of unrelated sentences? So from that example that we saw, so they will focus on certain entities. There will not be a lot of back and forth mentions, and everything should stand together. It should be coherent. So yeah, so this part, so that means there should be some structure, or the way the meaning is flowing, there should be some structure to that. So, so how to formalize this concept? So that again we'll see towards the last part of this topic. So coherence is the central theme of discourse. It models the logical flow in that discourse. I believe at an idea level, till this part you all are with me. Now, what are some intrinsic feature of a discourse, or intrinsic features of coherence? Is that there are certain things that you can observe when we look at the position, order, adjacency, context, and so on. So if you have a paragraph, it will typically have a nice opening sentence and a proper ending sentence. And it is true for any chapter that you see in a book, any email communication, any newspaper article, and like that. Then order, the different orders of the sentences. So if you jumble the order, sometimes it may lead to totally incoherent sequence of sentences, and sometimes it will be coherent, but the meaning will alter. Right? I said the magic words and a genie appeared versus genie appeared and I said the magic words. The meaning changes. Next, there's something called adjacency. The attributed material and contrasts are visible through the sentences nearby. So there is a gradual and sequential flow of information. Of course, there can be some long range dependencies or reference and so on, but in most of the cases, you will see that the information will flow from one sentence to another in a gradual manner. And sometimes it will be, some just taking forward the meaning that was there in the previous sentence. Sometimes this could be contrasting and so on, but there will be some local coherent structure also in that. And context is intended meaning can only be conveyed when understood in context. Okay, so the meaning of one sentence, or what meaning it actually triggers in our mind, is based on the surrounding sentences as well. So when we talk about contextual embedding, we said each word, the meaning of each word is actually influenced by the meanings of the surrounding words, but it's not only limited to that, limited to words. The meanings of sentences also are better conveyed when we look at it in the appropriate context. Okay, so as we said, coherence is the main characteristic of discourse. And how do we see that, okay, it is coherent or it's a proper discourse? So again, if you look back if you remember the examples that we said on the refer to the first slides, that Paris to Istanbul and as well as the piano store. So the first example where we said went to Istanbul because she likes spinach. So that was not our discourse, but the other one was, because the first one didn't make sense. Then, so whenever after looking at a discourse, we human understand that, okay, it makes sense, or it is relevant, or yes, the concepts, the sentences, everything hangs together well. And finally, it is coherent. So that's how we recognize discourse. And the central property here is coherence. So well, it is there, always there in well-written text. And then coherence detection plays an important role in many tasks where we need to understand, or we need to measure the quality of text. So there are some techniques which people are trying to devise since many years, like say essay grading. So there is an essay which has been written, and suppose we need to grade it in an automated manner. So their discourse and the meaning of different parts of the context could become very useful. So it falls as an extension of the how to understand discourse and how to apply it for downstream tasks. And then summarization, of course, summarization needs to have that property of discourse. So whatever finally we get, from that entire text, we are taking some portions, right? And there should be a flow of information properly maintained there. The final meaning should be conveyed. So that way it is again another example. Then detecting mental health. So in many cases where people face mental issues and they're not able to do certain things, often counselors, they ask them to write diary, write essays and so on. So, and then when they look at what the person has written, so that one thing that they try to see there is it coherent? right? Are they able to think in a coherent manner? Are they able to think in a proper logical manner? So it all gives some indication regarding how the brain is functioning. So as a concept level, discourse is a collection of coherent sentences, and a proper understanding of discourse is useful in many tasks. Okay, now meaning of coherence, the meaning and coherence of a discourse results partly from how its constituents relate to each other. So if you have a discourse, which is a passage, say, and its constituents will be the individual sentences and parts of sentences, the clausal structures, and so on. Now, how they relate to each other. So in that sentence, there will be many reference relations. One reference relation would be like co-reference. So different entities are referring to each other, which entity a referring expression refers to. So that part is one aspect. And there could be some discourse relations. So discourse relations sometimes can be informational and sometimes they can be intentional. It might be specified in an implicit manner. Again, we'll have some examples for that. So we have the first example here, which says so jewelry displays in department stores were often cluttered and uninspired, and the merchandise was, well, fake. As a result, marketers of Fox Gems steadily lost space in the department stores to more fashionable rivals, cosmetic makers. So if you look at these two sentences, the first one gives a reasoning and the second one is a result of that. And this connection is explicitly mentioned by looking at, by providing this construct. Then if you look at the next one, in July, the Environmental Protection Agency imposed a gradual ban on virtually all uses of asbestos. By 1997, almost all remaining uses of cancer-causing asbestos will be outlawed. So here also we have the same kind of structure where the first one specifies a reason and the second one is the impact or the result of that. And that is the connection between them. However, this connection is not explicitly mentioned here. It is implicit. So there are several different types of discourse relations. So some of them are mentioned here. So the first one, if you look at the parishioners of St. Michael and St. Angels stop to chat at the church door, as members here always have. In the tower, 5 men and women pull rhythmically on the ropes attached to the same 5 bells that were first sounded here in 1640. So it says that the parishioners of St. Michael and all angels, they come here, are at the church door, they stop. They stop. So they come here, they stop, and the next sentence that 5 men and women, they are pulling the bells. So there is some temporal connection here. So they have come here, they have stopped, and at the same time, people are pulling the ropes and ringing the bell. So this is an implicit connection, connector while, which we can assume that it is here. And these two things are happening simultaneously. They have arrived and stopped talking, and this thing is going on. So synchronous, and it's a temporal kind of relation. Then also, unlike Mr. Druder, Mr. Bridden appears to be in a position to get somewhere with his agenda. As a former White House aide who worked closely with the Congress, he is savvy in the ways of Washington. So here also we see a cause-effect kind of connection. So the because thing is implicit here. Next, if you look at the next one, the US wants the removal of what it perceives as barriers to investment. Japan denies that there are real barriers. So we see that, okay, there is some contradiction which is happening. There's some contrast which is being shown in this example. And but again, there is any, so there's an implicit, in that implicit bit is mentioned. There is no specific word or phrase here which says that these are contrasting, but when you look at the meaning, it becomes clear to you. So this is contrast, and it actually comes under the comparison category. Then if you look at this, not only do the actors stand outside their characters and make it clear they are at odds with them, but they often literally stand on their heads. So again, this is a conjunction. They do this as well as this. This another construct which glues together these two sentences. So if you look at any passage, maybe you take a newspaper article from today, you look at the sentences which are there, you'll be able to establish all these connections yourselves. And sometimes there will be, some corroboration there. Sometimes there could be uh, some implication. Sometimes there could be some contrast and reasoning and other things, as we see here. So right. So these are some kind of discourse relations which also try to maintain the coherence which is there in the text. Now, in order to judge, in order to look for, in order to estimate coherence, there are quite a few different techniques that have been proposed in the domain. So there is something called centering theory, which says that it tracks the focus of attention across adjacent sentences. So the thoughts should be centered on something, and then that center can gradually shift in a larger document. But in adjacent sentences, what do we see? There should be some centering happening. Then there could be syntactic form of references, uh, which could be like co-reference and so on. First and subsequent mentions. And then there could be lexical change, which is another extension of co-reference chains. So identifying and tracking topics within a text. So it says that uh, not only the same entity which is being, or same object which is being referred to again and again, but a lot of related things also are being referred to again and again. So examples will be there. So lexical chain is often discussed as cohesion indicator implemented in systems, but not use text quality terms. It is only for coherence estimation. So find all words that refer to the same topic. And for that, you need to have the correct sense of the words. So if you look at before winter, I built a chimney and I shingled the sides of my house. I had thus a tight shingled and plastered house with a garret and closet, a large window on each side. So when we read these sentences, we get a feeling that he's talking about a house. And how does this idea, or how does this uh, recognition comes? We see that, okay, chimney, shingled, sides, my house, plastered house, garret, closet, large window. All of these things are referring to the same topic. So the lexical chain for this will actually include these words: chimney, sides of my house, tight shingled, plastered house, garret, closet, large window. So it's not that each of them is referring to the same entity, uh, or is exact same as the large window and my house are not exact same, but they're referring to the same entity. They're parts of the same entity, and they're actually gluing everything together. So the lexical chain will have all these things mentioned together. And sometimes we may need to use knowledge structure on top of common sense knowledge. So yeah, so we may need to have some understanding that, okay, window is a part of house, and house needs clustering, or chimney is there in house. So these kinds of things could be there. Now, if you have some knowledge structure which guides in this kind of understandings, these models can actually benefit. Or common sense knowledge also can, if it can be inbuilt somehow, that can also be considered. So this is about lexical change, which says that if entities or part of entities, they are mentioned throughout. So if we can identify that, possibly that will be coherent. We are not abruptly jumping to completely new things. Then there is a concept called centering theory. So which says that, which deals with local coherence, because here we talk about a set of sentences which are surrounding each other. So how the flow goes from sentence to sentence, and it does not deal with the global structuring of the text. So it defines coherence as an estimate of the processing load required to understand the text. So there, what the observation is that in a complete passage, if you look at, the nouns will tend to differ. Now, suppose here in this example, we have focused on the nouns here. So there's some alignment issue here. They should be okay. Let me just fix it. Okay, so these are the different things, the different words that we are interested in, maybe the nouns. And suppose each column represents a sentence. Now, if we look at the role of this noun in each sentence, so firstly, we can see what are the sentences in which this word is appearing. So the word discourse is appearing in first sentence and second sentence. The audio slide. Yeah. Discourse, the study of how the meaning of a document is built out, the meanings of its sentence, built out of the meanings of its sentences. It is the intersentential analog of semantics, not intra-sentence, but intersentential analog of semantics. In this talk, we consider the following abstract problem in discourse. So the first sentence had a mention of discourse. The second sentence had a mention of discourse. However, in the first sentence, the discourse was the subject, and the second one, it's an it's not a subject, it's neither an object. Uh, yeah, so subject is we, and object will be like abstract problem in discourse. So not this exact thing. So that's what is captured, and it does not, the word discourse doesn't appear in the subsequent sentences. So against discourse, the first sentence has it and the role is subject. The second one, yes, this is present, but it's neither subject nor object. So another specific marker is there for that, and it's not there as part of any other sentence. Now, if you look at the third word, document, now in this, it says that the study of how the meaning of a document is. So it's there in the first sentence. Then given a document, we randomly permute the order of sentences. So this is the sentence number 3. And we have the full stop of this one. Then there is the sentence number 4. And fifth sentence says each model accounts for some aspect of the document. So we see the sentence, this word document in first sentence, second sentence, and third sentence, and everywhere it is present, but neither a subject nor as object. So that's what we see here, first, third, and fifth, and like that. So with that understanding, we can fill up a table like this. And then if we look at a table, we see that for the same word, it is appearing in nearby words, nearby sentences, and here nearby sentences. And if it is mentioned and then not mentioned for a long time, it rarely comes back again to talk about this and so on. On the other hand, if we simply jumble the ordering of the sentences, we get a structure like this. Now, in this toy example, it may not be visible very clearly, but in any large real document, if you take and try to do this, you will see that here the thing looks a bit disorganized, so unorganized. And the jumps that you see, so something was a subject, then it became an object, or something, then became a single mention, then not used again. So all these structures, nice structures, will not be here. So people had this observation, and there was one technique which was proposed, which was called entity grid method. So what we saw earlier is actually another entity grid. So here, what they do is the same thing what I discussed. So you have an input passage. Firstly, identify the individual sentences. Then secondly, you identify the phrases that you are concerned about, and which are mostly the entities or noun phrases. And along with them, you also mention what is the role of that word there, subject, object, neither, and like that. So yes, and then you create this kind of table. Now, given input document, you create a table. Now, from that table, you create a single vector. How is that vector? So if you look at word, so these here only the so these are the words, and here the sentence numbers are there. So it's the transpose of what we saw in the earlier slide. Structure wise, it is transpose. And so what you do is that what you notice here is that the there are 4 different types of tags, right? S, O, X, and none. Right? So if there are some 4 different tags or labels here, so 4C2, not 4C2, so there'll be transitions between this level. So if you look at the word department, so S to null is a transition, and there are many null to null transitions. For the word Microsoft, S to O is one transition, O to S is another transition, S to S is another transition, S to null is another transition, null to S is another transition. So that there could be different types of transition here. One type is S to null, another type could be null to S, another type could be S to S. So my question to you is, how many different types of transitions could be here? How many different types of transitions could be here?
Nine.
9. And yes, but how do you get that number?
S 3 into 3, where it could be SOX in the top. In the bottom, it can again be SO and X.
You're almost there. So it's not only S, O, X. I mean, if we consider this nulls also, it will be 16. But otherwise,
Yes,
if we
yes.
only restrict ourselves to S, O, and X, it will be 3. You're right. Okay. So from a passage, you construct this, and from here, you can have 9-dimensional or 16-dimensional vector, which counts how many such transitions are there for each time. Okay, so the first field there corresponds to SS. You count how many SS transitions are there in this, and we see only one transition. So we'll put a 1 under that column, and like that. So from an now for input passage, we get a 1-dimensional vector. Now this vector, now if you are given a data set where there are some passages which are proper discourses and there are some passages which are not, because the coherence is not there. Now this entire data set you can now represent as a feature and label kind of representation. So for this document, if it is coherent, we get the anyways we get the representation, that 16-dimensional representation, and the label is +1. And then you jumble the ordering here, you get a different matrix, you get a different vector, and the label is -1. So like that, you can construct a large database of examples or large set of training data. Then based on that, you can train a classifier model, a binary classifier, to to detect whether a given input is a proper discourse or not, or if a given uh, input shows coherence or not. So that is a simple algorithm about using entity grid for detecting coherence in an automated mode. Okay, so it's 9:43 or 44. So let us go for a 15-minute break now. We'll come back at 10 o'clock. Okay, so we'll wait for a minute and then we'll get started.
Sir, in the example which is there in the slide, so you mentioned that there are about 9 combinations, which is 9 edges will be there between S, O, X, and N. Then for a particular sentence, how do we actually represent them as embeddings?
It's a vector, not an embedding. So count
Okay.
for each different transition. So there are 4 labels here: S, O, X, and that blank or that hyphen. So from any 4 of them, it can come back to any 4 of them. Total 16 combinations are there. So we'll have a 16-dimensional vector. And suppose the first dimension is for SS, which means in one sentence it is the word is appearing as a subject, and the second sentence, in the next sentence, the word is again appearing as a subject. So count how many such instances are there. So here, uh, there's only one such example. So under that field, we'll note down one. Then suppose we have S to blank. How many are there? S to blank, we have 1, 2, 3, 4, 5, 6. So under that field, we'll have the count 6. So it's based on counts.
So it's kind of a matrix, co-occurrence matrix.
Not
The
co-occurrence matrix.
structure, not the structure, the n by number of word by the different S, O, X, and N by
No,
4, kind of that matrix.
it's not co-occurrence. It's how many transitions are happening. Transition means in one sentence, it is S, next sentence, it is blank. So S to
Okay.
blank is one transition. Then this is another transition, blank to blank. So like that.
So its size will be like token size into 16.
Again, I'm not getting why this confusion is here. So this you have got, and from let me just mm, so this is one possible transition. Then S to
Yeah.
O,
No,
another transition.
that we
It's
understood, sir, that there are 16 transition. So my question is that for every transition we count it, right? So like in one word, how many times a particular transition is there? So the question is on the representation. How do we represent it? Like for every token, now we have 16 representation, right? So suppose that a particular
wait. So S to S, we count in this entire matrix how many S to S transitions are there. So we have one here, right?
Yeah.
And there is no other S to S transition. So this is one. Then S to O, S to O, there is one here, and there is no other. So here also we have one. So like that, for that entire document, we'll get one 16-dimensional vector.
Yeah.
There is
So it's
yeah.
token size into 16, right? The dimension.
Why is token size coming into picture? How is
We are
token
doing
size coming?
we are doing it for every token, no? This
No, we are this is across the entire matrix. So S2 blank, how many are there? S2 blank. S2 blank,
Okay.
one, one, sorry, 3, 4, 5. So S2 blank is 5.
it's across the whole
Yes,
data set.
yes. Then suppose we have cross to uh, blank, not whole data set, not the entire document. X2, this is 1, 2, that's it, 2. So this will give the 16-dimensional representation for this entire document.
Okay.
You got it, sir.
Yeah, thank you, sir.
Okay, so let me then talk about the next method for measuring or detecting local coherence. So here, suppose we represent a sentence using some representation scheme. It can be anything. Okay, so ignore this part. Represent sentence using any kind of embedding that is of your choice. And then you take two sentences S1 and S2, and applying this technique, you get their vectors V1 and V2. And the similarity can be defined by any metric. Again, cosine is a specific instantiation of a similarity metric, but it can be any metric. And one simple technique could be like to represent the coherence of the text by taking the average similarity over the consecutive sentence pairs. So in your passage, suppose you have n different sentences, then you have n minus 1 consecutive sentence pairs, right? S1, S2, then S2, S3 till Sn minus 1, Sn. So for each consecutive pair, you take the similarity, sum them, divide by n minus 1, essentially the average of these similarities. And this can be one estimate of the coherence. But it is very simplistic, and sometimes there's a chance that even for non-coherent text, we may have high score, and coherent text we may not have high score. And these problems could be there because we are just having some. Yeah, it's a fairly simplistic model. So what additionally can we do? So that's the next part. So suppose we are talking about two sentences. Here we say S1, S2, two sentences. Here also we're talking about two sentences. And sentence encoder, there is sentence encoder which accepts the first sentence, and the same sentence encoder accepts the second sentence too. So although it is being shown as two different blocks, this is the same architecture or model. So you get representation S for the first sentence and the T for the second sentence. Now, what you do is you create a larger, wider feature vector by concatenating S, T, S minus T, absolute of S minus T, and field-wise multiplication of S and T. So like that, this becomes a larger. If the size of this vector as well as this vector was D, so this becomes 1, 2, 3, 4, 5, 5 into D. And this one you pass through an MLP, and whatever this MLP, so this MLP will finally produce a score, which is the coherence score. And you can also, so it's about modeling the task as a regression task, where the finally we want to get the estimate of the coherence. Okay, there's a number that we're predicting. But to train it again, we'll have to have something like accordingly the data set should be there, or yes, and it would also be something like a 0, 1 or binary prediction, like whether it's coherent or non-coherent. So in both the cases, what we can do is we can have a loss function which is of this nature. So what it says is that so this is the architecture, and then how do we train and how do we yes, compute the loss function so that by back propagation we can learn the weights. So theta is the parameter of the model. Assume that only theta comes only here, but you can also have a model where these parameters are also modified, but typically people will modify only this part. So from the collection, you take a document. From that document, you take a sentence SI. Okay, and then what you do is you randomly sample given SI another sentence S prime, which is not the consecutive sentence. So essentially, it should be S prime that is not Si plus 1. And so that means for the current sentence Si, we are having Si plus 1, with which we expect the coherence score to be high. And another sentence which is coming from part, which is S prime, which is a negative example. Okay. Now this model will take Si and Si plus 1 and give a score. And this model, the same model, will take Si and S prime, which is a negative example, give a score. And we define a loss function over this thing. So it could be like for a positive example, we expect the value to be higher, and for a negative example, the value should be lower. So accordingly, a loss function can be defined. And then you sum it over all sentences from the document and all documents. So this loss is contrastive in nature because we want higher score here and lower score here. And negative examples can be sampled uniformly. So that is here. And all right, so if you have that, then it is simple to train this network. So that is again one way of identifying local coherence. And now this same framework can be actually encapsulated, can be brought under a lot of larger different kinds of tasks to see how the model is able to discriminate better. See, for example, one could be like sentence order discrimination. What is that? Given a pair of sentences, you should tell whether they are adjacent or not. Okay, it is very similar to the next sentence prediction task. Then there could be something like sentence insertion. So here what you do is you take a document, you extract all the sentences S1 to Sn, and you take out one sentence Si. Now your document has n-1 sentences, right? And suppose we denote it as S minus I because I is not there, sentence I is not there. Now given this S minus I, you have to predict what is the place where this I sentence I should be inserted. Okay, so that prediction can be a task where the core network can be this. You can also train it for sentence reconstruction, sentence order reconstruction. So here you take a passage of size n, and you randomly jumble the sentences. You feed it to this network and finally tell the network to give the correct ordering of the sentences. So again, this can be another way in which this model can be used. So it's a simple yet very effective model. And yeah, I think so that's how it works. The point to be noted here is that although we are having a loss function, so we do not need any human supervision here. Using only these are all self-supervised tasks. Given data like a passage, we can easily create training examples for these tasks on our own. I mean, when you say on our own, in an automated manner without any human involvement. Okay, now given that we have a model for local coherence judgment estimation or discrimination, how do we evaluate the performance of that model? One is very simple, using manually annotated corpus we can do. The other thing could be like using self-supervision. When each of the tasks that I mentioned can also be considered or can also be used for this and for evaluating this kind of coherence. Right? So suppose you say that, okay, this is my model for coherence estimation, and then to this model you give this task of sentence order discrimination. So is it able to discriminate that, okay, given a pair of sentences, whether they are coherent or non-coherent? So that will tell whether they're adjacent or not. And similarly for this one. So ideally what we expect is that if the sentence is inserted at the correct place, then the coherence score that we get out of that will be higher as opposed to if it is put at the incorrect place, and like that. So
The task that we are training this model for, it produces binary output, right? 0, 1, the coherent score during the training time.
So this can be real numbered scores.
Then
it's up to you actually. You can model it as a
Okay.
classification task or a regression task, and both are possible technically.
So in that case, we manually have to assign some scores to different pair of sentence based upon the coherence.
what you can do is on top of, so suppose this is f theta.
Yeah.
And on this f theta, you can have this loss function. So finally, our data set has what is consecutive, what is not. So it will just tell that, okay, if there are unrelated sentences, their score will be less as compared to related or consecutive sentences.
Thanks, sir.
So this loss is for discrimination, right, sir? Will it work even for insertion and reconstruction?
So you can model it accordingly. So so you can train a network for this one and then evaluate for this task. So their loss function need not change. And you can make use of this for insertion task where the sentence is inserted at the correct place. In this case, you can expect this loss to be lesser. And yeah, if it is incorrect, then the loss can be higher. So this minor tweaking might be needed for the other things, but it directly works for discrimination.
Okay, sir. Thank you.
Okay, now let us talk about a larger discourse. So there are different units of discourse. So the one way in which we are considering it was the sentence level, right? That these two sentences, whether they are coherent or not. Our text can also be segmented into a minimal units or spans. So these are called nuclearity. So again, there are some examples in the subsequent slides. So there are some spans which are more central to the text's purpose. So these are mostly about the clausal structures that we are talking about. So if you remember, we said that a discourse actually tries to capture sentential, or across sentential flow of meaning. Right? However, there can be a larger sentence which can be split into shorter clauses, and these clauses convey some concrete meaning. So that way, it can be at the clausal level also. So some spans are more central to the text purpose, whereas some others are secondary. So I'll just give examples. So Jen took a train from Paris to Istanbul. She had to attend a conference. So for this action, or for this pair of sentence, for this sequence, the major thing that the person is trying to convey is that Jen took a train from Paris to Istanbul. That's the main thing, and this becomes a reason. So which becomes a satellite. The core thing is this, which is called nucleus, and this will be satellite. And there's a connection, nucleus to satellite connection, satellite to nucleus connection can be labeled as a reason. Then suppose you have this one. Dorothy was from Kansas. She lived in the midst of the Great Kansas Prairies. So again, here is the central thought, and this is some kind of elaboration. Where in Kansas she used to live. So again, there's an edge from satellite to nucleus, and the level of that edge could be elaboration. Next, the satellite, Kevin must be here. His car is parked outside. What does it mean? So this is again the core thing, and these are supporting evidence. So again, another connection, and the label is evidence. Then there could be things like analysts estimated that the sales at the US stores declined in this quarter too. So here in the earlier sentence, in the earlier examples, there were two different sentences and there were connections between them. So one sentence was nucleus, another was satellite. And in this case, it's a single sentence, but there are two parts here. One is nucleus, another is satellite. So what is the main concept here? That US stores, the sales there has decreased in this quarter. Now that is the central idea, that the message that the person is trying to convey. And it also gives you some attribution. Who has said that? So this is again nucleus, the satellite, and attribution. Now next example, again a clausal structure where we have a semicolon here, which is a more independent sentences. So Billy Bones was the mate. Long John, he was the quartermaster. Now here, what we say is that both are nucleus, both are information, parallel information to be shared. So this is a list. So these are in some relations in the discourse, and we also looked at some other relations like implicit or explicit relations for temporal and synchronous connection, then contrast and other things. So they are also some other kind of relations. So in a discourse, these relations could be there, and there is a hierarchy of relations. In fact, that's how the sentences, their meanings that flow through. So if you this example we saw, Kevin must be here. His car is parked outside. So this is the nucleus. From satellite to nucleus, there is an edge, and yes, the label is evidence. And if you think that you have been injured by being in this study, please let the investigator know the right way, right away. So if you think that you have been injured, there is the nucleus. If you think it's the attribution, so there is a connection between this nucleus and attribution. And this thing together becomes a condition for this action. Please let the investigator know right away. So this becomes a hierarchy. Now, this example is from a recipe that peel oranges and slice crosswise, arrange in a bowl and sprinkle with rum and coconut, chill until ready to serve. So each of them are nucleus, they're parallel list, and essentially, although it's a parallel, there is a sequence among them. So this is again something. So yeah, so that is how, if you are given a longer text, how you can connect them together. When you say longer text, I mean a few sentences. So this kind of structure you can get. Now this structure is called a rhetorical structure tree, or RST. So rhetorical structure tree for a given input will actually try to get a tree-like structure where you have the different components of the individual sentences and the sequence of sentences and how they are connected with each other. So this is one example. And given a text, given an input text, the way in which you can come up with this rhetorical structure tree can be done in many ways. One simple way is shift reduce parsing. So today we'll not talk about shift reduce parsing. So when we talk about parsing in the next lecture, so there we'll have some examples of shift reduce parsing. So, but again, that means that we need to have some data sets like this from which these models can actually learn. So, and there are such data sets. And here we also mentioned about elementary discourse units or EDUs at some point of time. Yeah, so this units of discourse, the text can be segmented into minimal units or spans. And we saw that, okay, this nucleus and satellites, typically these are the discourse units. So given a sentence or given a paragraph, then the first task becomes to identify these elementary discourse units so that we can, in the next step, try to build the connections among them. If here Mr. Rambo says that a 3.2-acre property overlooking the San Francisco Valley is priced at this much million because the late actor Errol Flynn once lived there. Okay. So these could be the 5 elementary discourse units here in these sentences. So given a sentence, how do we identify these elementary discourse units? It can also be considered as a shallow parsing. So the input is given and then you pass it to a contextual encoder. And for each token, you get a representation. And for this representation, you can have multi-layer kind of architecture also. And from this, finally, you make it a 0 or 1, indicating whether it's a part of the previous or a this EDU which is already continuing, or we start something from here, or we end something from this point. So in this example, Mr. Rambo says that, so at that, we begin a new discourse. It is a change of discourse. So this is 1. You can say that, okay, Mr. Rambo from here also a new unit begins, so it should also be 1. Even that is okay. So I think the way they modeled is whether there is a change in the discourse. But otherwise, if you have this as 1, even in that way, it should be okay. Just you have to train the model with that assumption. So this was about elementary discourse unit. So step by step, if we look at local discriminant, local coherence discriminator, and then we looked at something which is goes beyond and gives us a tree, a structured tree. And then there's something called argument mining. So this we will not cover in detail, but there is a paper that will point you to. And yes, and some we'll try to at a high level cover what that paper talks about. Well, this talks about RST parsing, but yeah, I think we have covered it already. So task is to create the RST from the input text. It can be done through shift reduce parsing. It maintains a stack, items in the stack. So this, okay, this actually requires the understanding how the shift reduce parsing occurs. So if I have time at the end, I'll just bring up that slide and explain. Otherwise, at this point, just assume that it can be done in this manner. Okay.
What exactly is parsing?
Okay, parsing
What?
is something like you have a free flowing sentence and then you try to identify some structure from it. Now this structure can be at a tree like thing, like suppose you have a sentence and you try to say which word depends on which other word. So like that, there can be some connection. Or it could be something like, okay, given this sentence, there is, or I think this example could be more direct, like when we give command line arguments, right, for a program. So, or suppose we are using the Linux terminal and we are running a code from the terminal, and then we are giving the different command line arguments. So the method tries to determine which argument is, I mean, yeah, so what value is for which argument. So that is called command line parsing. Then suppose you give a SQL query to a database. Now database, when it looks at it, it tries to identify a structure from there. So for example, select select name from table where course ID is equal to CS5803. So it tries that, okay, this is the table name, this is the column name, and this is the condition that I need to match, and all these things could be there, right? So this is another way of getting some fine-grained and structured information from the text. In some cases, the structured information will come as a tree. In some cases, only at this level, like a shallow structure can be there. Like, okay, this command line argument is the file name, this command line argument is the number of lines in the file, and so on.
So in a way, what we discussed in co-reference and some part of incoherence, like we saw the temporal uh, tree-like structure in the sentences and documents. So those can also be understood as parsing.
Co-reference, no.
Like it, or some other in a long document, some words refer to a referent which are already defined previously. So
That may not still, I don't know whether that will be called as parsing, but this tree, this structure, if you get this, definitely a parsing. And mm, but co-reference will not be.
okay.
Sir, I think parsing is limited to capture syntax of a sentence or the grammar.
It
There
can
are
be
other types of
that
parsing,
also.
like
Can be
semantic
beyond
parsing. Yeah.
that also. So I think the sequencing got incorrect. Really. The parsing should have been covered earlier, but yes, I think some of these queries will be resolved in the next class when we talk about. So it's more about the connection across various components in a sentence. Sometimes it could be at syntax level, sometimes it could be at a semantic level as well. So here we also, in this RST, semantics is also captured. And the co-reference resolution, it's a very minimal, only a few things, only a few subset of phrases actually uh, participate in that process, although the entire text can have many more red words. So that way, it's not actually parsing. Uh, Yeah, but there could be other parsing techniques where we are actually interested in identifying. There are some shallow parsing also, like the name entity recognition can also be considered as a shallow parsing. But here, against each and every token, we assign whether it's a part of an entity or not. But in codefend is mostly limited to a subset of phrases only. Because, yeah.
Sir, this tree do we create for one document or like for some chunk of sentence?
It's from a chunk of sentences. So if you have a very large document, there RST, it may become a forest as such. I mean, no. So if there is a paper where there are many sections separately, yeah, it will not be a very dense tree like this. It could be like very small trees which are somehow interconnected. There can be some dangling trees. So typically it's for shorter documents, shorter passages.
And this is created manually or do we learn to create this from the sentence?
This is automatic.
Oh, so model creates it automatically.
Yes. And there are some data sets also for training those models.
Okay.
So it will start by identifying the chunks or components, which will be the individual nodes, and then how to keep combining them step by step. So that part will be the learning part. Will be this identification is the first part. The next part will be that how they should be combined.
Got it.
And how they should be combined, it also depends on what are the entities that we're, or what are the fragments that we're going to combine, and accordingly, what should be the level of that age or that combination, like elaboration or background or contrast or whatever. Okay,
Thank you, sir.
so RST parsing. Now, global coherence is the discourse must adhere globally. So consider a story. So it can be this Harry Potter novel. There is something here, and after 300 or 400 pages, there is something. Still, there should be some connection, some flow. We can talk about some kind of a chart sheet which is say 8,000 pages long. Will still be connections. So although I think these kind of techniques are not applied or have not been, yeah, it's very difficult to do that. But ideally, when we talk about global coherence, we look at much the entire document into consideration. So it must adhere globally, scientific articles, patents, stories, so on. And the possible routes are global coherence structures. And one example is that is argumentation structure. So where it identifies the relations between sentences. And when we talk about relations, if it is argument mining, we talk about the different claims, the premises, and whether something is refuting, something is supporting. So these kinds of structures we try to identify. So this is one example. I'll go to the paper and just show you the snippets from there. Uh, so what it says is that mm, it's a long 42-page paper and coming from a linguistics community. I'll just go to the relevant part. It talks about discourse analysis, where the kind of discourse, the kind of connection they try to find is identification of argument structures. So again, discourse analysis aims at identifying elementary discourse units and the discourse relations among them. So there are many ways for doing this for so PDTB is a tree bank, collection of trees for discourse identification. There's a theoretical background, argument diagramming. There are different ways in which the arguments can be there. In many mathematical examples, what we see is that there's a sequence in which we try to prove, right? Step 1, step 2, step 3, like that. So argument, and there can be sequential connections. From this step, we come to next step, and so on. There could be convergent arguments with 2 different steps. They connect with the same, same argument. So this is okay. There's a serial argument. There's a basic argument 1, and this and you can chain together many such things for serial arguments. Then given one claim, we can break it into 2 parts and try to prove each of them separately, and so on. I mean, there can be some structures here between which the real difference may be a little difficult to guess, but overall, I think they explain it in a formal manner inside this paragraph. Okay, so they have some examples regarding. Yeah, so here they talk about, since they're talking about argument finding, they talk about claims, subclaims, and premise, subpremise, these kinds of this kind of nature. Yes, so this is the. Here we have a couple of snippets from the document on which they present this example, and later they talk about methods. So ever since researchers at the Roslin Institute in Edinburgh cloned an adult sheep, there has been an ongoing debate about whether cloning technology is morally and ethically right or not. Some people argue for and others against, and there is still no argument whether cloning technology should be permitted. However, as far as I am concerned, cloning is an important technology for humankind, since it would be very useful for developing novel cures. So here, this is an argument, this is a claim. Cloning is an important technology for humankind. That's the person's thought that he or she is putting directly. And the reason is, since it would be very useful for developing medical cures. Now, this is again a claim, but this claim is trying to support this major claim. But again, this is a claim at this point. Then it continues. First, cloning will be beneficial for many people who are in need of organ transplants. Again, a claim statement, simple statement, a claim. Cloned organs will match perfectly to the blood group and tissue of patients. So this is a reasoning, which is a premise for the claim. Since they can be raised from cloned cell of the patient. So this premise 2 is supporting premise 1. So now we see that, okay, there's one piece of text that is supporting another piece of text. In addition, it shortens the healing process. Usually it is very rare to find an appropriate organ donor. By using the cloning in order to reach the required organ, the waiting time can be shortened tremendously. So like that. Then they have, therefore, cloning animals enables novel developments in science. Another new claim has come, but they have backed it with some premise. Scientists use animals as models in order to learn about their diseases. So these they're already known from references. So that is a premise 6. So like that, if you continue, you'll get an argument tree structure like this. So there is a major claim, and there was claim 1, which was connecting to major claim. So that we see here. This is the major claim, since it would be beneficial. So major claim 1, since claim 1. So claim 1 is supporting the major claim 1. So claim 1, this dark triangle means supporting major claim 1. Then the body paragraph 1 has 5 premises: P1, P2, P3, P4, P5. Cloned organs will match perfectly. This is P1, then P2, P3, P4, P5. And 1 and 2, there is a relation between that. cloned organs will match perfectly to the blood group and tissue of patients since they can be really strong. So premise 2 is supporting premise 1, and this is the discourse connector. And then there are things like it shortens the healing process. In addition, it shortens the healing process, so it's a separate thing. It is very rare to find an appropriate organ donor, and by using cloning, this can be done. So premise 4 and premise 5 are parallel, and they support premise 3. So P4 and P5 will lead to P3, and P1 and P3 together will support claim 2. So that's what we see. P4 and P5 connects with P3, PT supports P1, and they together support for claim, and like that. Now, if you have paragraph 3, uh, mm, admittedly, cloning could be misused for military purposes. For example, it could be used to manipulate human genes in order to create obedient soldiers with extraordinary abilities. So, premise 9 supports claim 5. However, because moral and ethical values are internationally shared, it is very unlikely that cloning will be misused for militant objectives. So, whatever claim it was said that the claim could be misused, and now it is saying that it is very unlikely that it will be misused. So, this is trying to disagree or refute with claim. So that's what we'll see, that claim 5 is refuted, this blank circle, by premise 11. And like that, in that way, you know, a broader understanding of the document structure can be obtained. So this is about argument, and they have created a corpus for this task. They have then talked about interpreter agreement and so on, and they've analyzed this one, the final corpus statistics, and then they provide a model for parsing this argument structure and identification model, component classification, the relation identification, and then tree generation. So identify the components, then you classify them, which one is claim, which one is premise. Then you try to see which one supports, which one refutes, the connection between them. And then from that, the tree generation. And finally, the stance recognition. Like, so this is the other high level approach. Steps in the high level approach: argument component identification, then classification, component classification, and then relation extraction, tree generation, and then stance recognition. So, yeah, I mean, it's another interesting piece of work when we talk about global coherence. So this one, if you look at the first page, sorry. Yeah, so from computational linguistics. So this was about discourse, and there are some further references that I've added from recent. So learning sentence embeddings for coherence modeling and beyond. So this is and sentence ordering and coherence modeling using recurrent neural networks, and they're fairly recent, not very recent, 6 years back. And then there is something automated evaluation of written discourse coherence using GPT-4. So nowadays people are also using large language models for understanding different aspects of coherence. So, or this one tries to see possibly identifying the coherence from whatever is generated in by these models and so on. So there are, there will be more such papers. This is a difficult, one of the very most difficult tasks in this. It deals with pragmatics. So yeah, typically this comes after parsing. I think certain parts would have been easier understood had we covered parsing earlier. So that brings us to the end of the topic for discourse. Any questions?
Sir, these when we were saying about nucleus and satellite tagging, they are like annotations, is it?
Nuclear and satellite. Yes, yes.
Okay.
This is level 1 classification or labeling.
Okay.